Assalamualaikum warahmatullahi wabarakatuh. Today I will explain about control and instrumentation group assignment. Before I continue, let me introduce our team member. The first one is Muhammad Irfan Fidaus bin Johari. The second one is Muhammad Akwa bin Muhammad Hafiz. The third one is Muhammad Amiruddin bin Jalaluddin. And the last one is me, Muhammad Azruazin bin Azhar. So let's jump into introduction. Uh, Introduction. Unity feedback control system are commonly used in engineering to ensure stability and desired performance. Analyzing their dynamic response and steady-state behavior is essential for understanding how they react to different input. Time domain specification like peak time, settling time, and percent overshoot along with steady-state error analysis provide key insight into system accuracy and reliability. So the first one is objective and scope. The study aimed to analyze the dynamic response and performance characteristic of a unity feedback control system with a specific forward path transfer function. So the second one is analysis and method. Time domain specifications such as peak time, settling time, and percent overshoot for a step input were calculated and validated using MATLAB and Simulink. Steady-state error were also examined for step, RAM, and parabolic input. So the third one is result and comparison. Theoretical results were compared with simulation outcomes to evaluate model accuracy and system stability. So the next one is objective and goals. Objective, the overall objective of this project to analyze and validate the dynamic performance and stability of Unity feedback control system using both theoretical and calculations and simulation tools. Uh, Example, MATLAB and Simulink. The goal is to ensure accurate modeling, evaluate system behavior under various inputs, and confirm its reliability for control application. So the first one is analyze time domain performance. Determine key time domain specifications such as peak time, settling time, and percent overshoot for given unity feedback system. The second one is validate through system. Obtain and analyze system response using MATLAB and Simulink for different input types, and compare this result with theoretical calculations. So the last one is evaluate accuracy and stability. Calculate steady-state error for step, RAM, and parabolic inputs. Assess system stability and verify consistency between theoretical and simulated outcomes.
Assalamualaikum. My name is Muhammad Akwa and I will be presenting about time response analysis. So as we can see, this is our theoretical calculation part where we solve using the equation to get the peak time, setting time and percentage overshoot. So for the peak time, it's zero point 0.6, while the setting time is 2.1 second, and percentage overshoot is 22.4%. So this is our simulation part where we can see the result for our unity feedback system for k equals to 200. We can see that the peak time is 0.7 second, percentage overshoot is 27%, and the setting time is 2.1 second. And for the last part is comparison result between calculation and simulation. So as we can see, the peak time for the calculation is 0.64 second, while the simulation is 0.7 second. The setting time is 2.1 second, while the simulation is 2.127 second. The percentage overshoot is 22.4, and for the simulation is 27.95%. The calculated and simulated results show similar trends, confirming the accuracy of the system model. The setting time values are very close, indicating a good agreement. However, the simulated percent overshoot is higher than the calculated value. This is because the simulation includes the effect of non-dominant poles. Overall, the simulation validates the theoretical analysis with minor difference.
For stability in closed system simulation part, the plot shows the locations of poles in the complex S-plane which directly determine system stability and dynamic behavior. Interpretation of the pole zero map. All the poles lie in the left half of the S-plane, negative real part. Since there are no poles on the imaginary axis or right half plane, the system is stable. Okay, for the stability in closed system, theoretical calculation part, theoretical stability analysis of the closed loop system using Rod-Hewes criterion. Starting from the characteristic equation, the Rod table is constructed using the coefficient of polynomial. From the complete Rod array, it is observed that all elements in the first column are positive and there is no sign change in this column. Okay, for stability in closed system, comparison result, the calculate and simulate results for the closed loop system stability are identical. Both methods show one real pole at negative 15.23 and a pair of complex conjugate poles at negative 1.89 plus minus 4.9 J, all located in the left half of the S-plane. That confirms that the system is stable.
Hi, my name is Muhammad Ifan Fidaus. So here we have the simulation results for the steady state error under three different inputs, which are step, ramp, and parabolic. On the left, for the step input, the block diagram shows the system configuration, and the graph below indicates that the error settles at approximately 0.512. In the middle, for the RAM input, the graph shows the error increasing steadily, reaching about 25.71 during the simulation period. On the right, for the parabolic input, the error grows rapidly, reaching 645.3, which is extremely large. These results confirm that the system performs well for step inputs but struggles significantly with RAM and parabolic input. So for this slide shows the theoretical calculations for steady state error using static error constants. For the step input, we calculated the position error constant Kp and found the error to be 0.512. For the RAM input, the velocity error constant Kv leads to an infinite error, meaning the system cannot track RAM inputs. For the parabolic input, the acceleration error constant Ka also results in an infinite error. These calculations confirm that our system is a type 0 system, which explains why it only handles step inputs effectively. Finally, this slide compares the theoretical and simulation results. For the step input, both methods agree at 0.512, showing good accuracy. For the RAM input, theory predicts infinite error, but simulation gives 25.71 due to the limited simulation time. For the parabolic input, theory predicts infinity while simulation shows 645.3, again because of time constraints. Overall, the results are consistent with control system theory. A type 0 system has increasing steady state error for higher order inputs. To improve performance, we would need to add integral control such as PI or PID controllers. That's all.
Okay, for the last one is conclusion. Conclusion: the analyzed unit feedback control system is stable and demonstrate dampened oscillatory response for step input. Both theoretical and simulation results for time domain specification were closely aligned, confirming the accuracy of the analytic model. However, due to its type 0 configuration, the system show limited tracking capability to RAM and parabolic input. To enhance steady-state performance for such inputs, incorporating integral control is recommended in the future design. Thank you so much.